Solving inequalities work just like solving equations. There's only one or two little tricks we have to do, and I'm also going to graph these on a number line as well. So I'm going to get right to it here, starting with number 1. So we've got 2x minus 1 is greater than or equal to 13, and I want to solve this for x. So just to kind of show you guys the connection here, it never hurts to draw your lines on either side of the inequality bar just to help you out. And we're going to start by moving the 1 first. I'm going to assume you already know the basics of how to solve an equation, so I'm not going to get too wordy here with how I'm solving these. So I've got 2x is greater than or equal to 14, and then if I divide by 2, I should get that x is greater than or equal to 7. Remember that this sign right here says greater than or equal to. This sign over here would say less than or equal to. The way I remember it is that less than looks a little bit like an L on its side. Greater than looks backwards, so that I don't think about that one as being looking like an L. So we got x is greater than or equal to 7, and that would be our answer to the solution. Now, what we are going to do is graph this on a number line. Your teachers may have you, graph more numbers than this. For me, I usually just graph the number I'm looking for. So I'm looking for 7 here. Since x has to be greater than or equal to 7, since it's equal to it, I'll put a closed dot. If there was no line underneath, I would make it an open dot. And then this should shade to the right. We need all the numbers that are bigger than 7, and all the bigger numbers are out towards the right, whereas all the smaller numbers are to the left. So that would be my answer here. I just solved the first one, and I just graphed it, so I'm moving on to the next one. Okay, number 2. This one, a little bit easier to solve, but there is one thing we have to remember here. I'm going to divide by -3 on both sides of the inequality bar, and that will leave me with x is, and I'm going to write this as incorrect, but I'll write it this way first on purpose. A common mistake is that people forget when you divide by a negative number on both sides. Notice that this 3 that we divided by is negative. I have to flip this inequality sign around, so I actually got to fix that here. This should no longer be greater than. Now that I divided by a negative on both sides, it should read less than. Okay? And if I go ahead and I graph this on my number line, I'll have -6. I'll put that there in the middle. I'm going to graph an open circle because that says less than, not less than or equal to. It doesn't have this bar underneath it. Otherwise, it would be a closed dot like this. So it will be an open circle, meaning that -6 is not included in the solution, and I need to shade towards the smaller numbers, which are on the left side. Okay? The other way to remember that is that it almost makes a little arrow pointing towards the left. Here it makes an arrow. This sign makes an arrow pointing towards the right. Now that only works if the x is on the left side. Okay, here we go. So next one, we're going to add 1 to both sides to solve this, and we'll get 2/3 x is less than 12, and then I'll multiply by the reciprocal. You could also divide. You could also divide by 2/3. That would work too. We'll multiply by 3 over 2, and now these will cancel. We'll get x is less than 12 over 2 is 6. 6 times 3 is 18. And if we start here, I'll put the 18 on my number line, and it'll be an open circle shading towards the left side because this is less than. So again, there's an invisible arrow pointing towards the left. Again, that only works if we have the x on the left side of the inequality sign. And we are almost there. We got one more to go. So I'm going to start here by distributing my -5 in. So I'll have -5x plus 3 is greater than -5x, minus 20. And remember that for these types of problems, we need to get all the x's to the same side before I can really start to solve this. So I'm going to move the 5x over to this side by adding it. And what you actually notice here is that the x's cancel, so all the x's are gone, and we're left with 3 is greater than -20. And if we look at that, that actually is a true statement. So first thing to notice is all the x's are gone, and we're left with something that is a true statement. 3 is bigger than -20. When this happens, just like when we solved equations and we got something like 3 equals 3, that was a true statement, we would write all real numbers. So our solution here is going to be reals, or all real numbers. Or you could also, again, so all these, you could also use the symbol for all real numbers, which is this kind of double-lined R there. Okay, so the back of the R is double-lined. Now, you might think for a second, well, how would I shade this on a number line? What all real numbers means is that any number that you plug in to this expression or inequality is going to make this true. So if we plugged in 0, that would make it true, and I'll leave that to you guys to check it. If we plugged in 5, -1, -20, 2.5, anything we plug in for x will make that true, so we have to shade the entire number line here. So any number is going to work. Okay? And the only other thing I would add here is that if this were an untrue statement, like if we solved this whole thing, let's say that this problem, we solved the whole thing and we got something like 5 is greater than 10, well, that's not a true statement. You might guess that that would be no solution. So if you get with an untrue statement at the end, it would be no solution. And if you were to graph this on the number line, no number would be shaded, because what no solution means is there's no real number or there's no value that's going to ever give you something that would make this inequality true.